Hello, welcome to the Bakwas channel for self-paced tutorials on robotics. This presentation demonstrates a basic linear travel movement for a holonomic drivetrain. A robot can travel a preset linear distance by keeping track of the rotation or fractional rotation of the motor that is attached to a wheel with a known diameter. This metric is a useful introduction for youth team members embarking on performing precision movements with robots. The wheel will travel a preset distance specified by the user at the start of the op mode. In this simple mode of operation, the linear movement will not be corrected for deviation from the planned path. Linear travel, forward or backward, is the introductory step in controlling the movement of the robot. While it may not be practical to keep the robot in a perfectly linear track for several reasons by the application of constant speed, this op mode does not perform any corrective action. The target and speed are set for each motor independently. The robot immediately moves to the target destination under these conditions. All motors must reach their respective target counts or ticks before all motors are stopped. In this tutorial, it is not so much a matter of reaching a distance, but rather the motors spin until the number of counts or ticks are reached for all motors. There can be factors beyond this simple op mode that prevent the robot from traveling the distance very precisely. Two factors that come to mind are friction properties between the wheel and field surface, and inaccuracies in counting the ticks owing to tolerance issues with the corresponding Hall effect sensor for the errant encoder. Most motors for FTC robots have encoders to support the control of rotation in these motors. There is an excellent YouTube video from ServoCity, a GoBuilder subsidiary, that explains the principles of the type of encoders used for FTC robots. This tutorial assumes that the viewer has a basic understanding of the principles to follow the calculations presented in the succeeding slides. Quadrature encoders for robot motors work with two out-of-phase channels by using the difference in the phase of the two channels to determine the direction of rotation. The two channels are typically 90 degrees out of phase, which means that they are at opposite points in their cycle at any given time. When the motor is rotating clockwise, the signal on the first channel will be high, while the signal on the second channel will be low. When the motor is rotating counterclockwise, the signal on the first channel will be low, while the signal on the second channel will be high. This difference in phase can be used to determine the direction of rotation by comparing the signals on the two channels. If the signal on the first channel is high, while the signal on the second channel is low, then the motor is rotating clockwise. If the signal on the first channel is low, while the signal on the second channel is high, then the motor is rotating counterclockwise. In addition to determining the direction of rotation, the quadrature encoders can be also used to measure the speed of rotation. This is done by counting the number of times the signal on either channel changes state. The number of state changes per second is proportional to the speed of rotation. Quadrature encoders are a valuable tool for controlling robot motors. They provide accurate information about the direction and speed of rotation, which can be used to ensure that the robot moves smoothly and precisely. Some additional benefits of using quadrature encoders for robot motors are high resolution. Quadrature encoders provide high resolution, which means that they can accurately measure small changes in the position or speed of the motor. Reliable. Quadrature encoders are reliable and can withstand harsh environments. Cost-effective. Quadrature encoders are relatively cost-effective, making them a good choice for budget-minded projects. The image on this slide is from Robotics documentation. Rev has two motors where this encoder arrangement is present. A 12-pole magnetic quadrature encoder is installed on the rear of both HD hex motor and core hex motor. The output shaft of the motor extends from the rear of the motor case, and a multi-pole permanent magnet is attached to the shaft. There are two Hall effect sensors marked A and B mounted next to the magnet at 90 degrees to each other. As each of the 12 poles passes across one of the Hall effect sensors, it creates a change in the magnetic field, causing the sensor to generate a measurable voltage signal. Every time the output goes through all four distinct combinations of output signals, it's called a cycle. See the labels marked A, B, C, and D in the top image. Encoders have different cycles per revolution, CPR, based on the number of poles on the magnet used. The CPR specifies how many cycles are generated for one complete revolution of the encoder shaft. An example output from one complete rotation of a 14 CPR encoder is shown in the second image. A 14 CPR rotation encoder may also be referred to as having 14 rises on channel A. Encoders are mounted to the motor shaft, not the gearbox output shaft. So for a motor with a reduction gearbox attached, this is less than one full output shaft rotation. One reason to use CPR to define an encoder rather than the commonly used pulses per revolution PPR is when the encoder signal is decoded by the microcontroller. It is possible to do 1x, 2x, or 4x decoding. For 1x decoding, the microcontroller would only count the rising signal on a single channel, while for 4x decoding, each rising or falling edge for both channels is measured as a count. Although 4x decoding is one of the most common methods, because it's based on how the electronics decode the signal from the encoder and not on the encoder hardware itself, it's not an ideal method of defining the encoder hardware specifications. Counts per rotation, CPR, is a measure of the resolution of a quadrature encoder. It is the number of times the encoder's output signal changes state as the encoder shaft rotates one full revolution. For quadrature encoders that use Hall effect sensors, the CPR is calculated by counting the number of times the two Hall effect sensors generate a square wave as the encoder shaft rotates. The two Hall effect sensors are typically 90 degrees out of phase. So each time the shaft rotates one full revolution, the two sensors will generate a total of 4 square waves. The formula for calculating CPR for a quadrature encoder that uses Hall effect sensors is shown on the last line of the slide. The linear distance value can be used to track the movement of the robot or to control the robot's movement. Some additional considerations for converting linear distance to travel using counts per rotation of a quadrature encoder using Hall effect sensors in a robot motor. Be sure to calculate the circumference accurately using accurate measurements of the wheel's outside diameter. Be sure to have a verified value for counts per unit distance with sufficient accuracy. Be sure to use the correct units. Wheel diameters are generally expressed in millimeters, while FTC prefers inches or feet for linear dimensions. Go Builder provides the numbers for counts per revolution directly on the respective data sheets of their motors. Use your wheel diameter to obtain the counts per inch value. Then plug in this value in the op mode. Rev uses cartridges for its planetary gears, and the values will depend on the gear configuration. Again, Rev publishes the corresponding numbers, but for the permutations of the cartridges, some nominal calculations are required. Also, be careful about the precise gear ratio calculations. For example, using the 5:1 and 4:1 cartridges produces an overall 20:1 gear ratio, but the actual number is around 18. You can verify this assertion from the data tabulated in the Rev Online documentation. For learning purposes, the next few slides illustrate the basic calculation steps. Once again, depending on the choice of motors, these calculations may be redundant. This slide illustrates the Go Builder datasheet for the 5203 series Yellow Jacket planetary motor with a 19.2 to 1 ratio gear motor. There are two planetary gears in the motor, and the formula for the effective gear ratio is provided by the vendor. The motor has a quadrature encoder with Hall effect sensors. 4 discrete phases are emitted by the encoder during the rotation of the motor. In the absence of more detailed documentation, we could check with Go Builder technical support, of course. Our assumption is that there are 7 rises of a channel in this common encoder. Therefore, 7 times 4 provides the multiplier for the gear ratio that results in multiplying the effective gear ratio by 28. This motor's encoder generates 537.7 counts or ticks for one revolution of the external axis of the motor. This slide illustrates the calculation of counts or ticks per rotation of the output shaft of the motor. In this example, the Rev HD hex motor has 2 planetary cartridges, 5:1 and 4:1, resulting in theoretical equivalent to 20:1 gear ratio. However, the effective gear ratio for the 5:1 planetary cartridge is 5.23:1 as published by Robotics. Similarly, the 4:1 planetary cartridge has an effective gear ratio equal to 3.61. Multiplying these two effective gear ratios provides the number 18.8803 for the overall gear ratio when these two specific planetary cartridges are used. Notice that the effective gear ratio is slightly different from the theoretical number. Rev has published the cycles per rotation of the encoder shaft as 28. Multiplying this number by the effective gear ratio provides the counts or ticks per rotation of the output shaft as 528 approximately. This slide is a pro forma template for the calculation of counts per inch for the motors from any vendor. These equations are used in the following two slides to illustrate the calculated values for two vendors with their respective popular motors. Most of the starting values are documented, but the number of rises of channel may not be clearly documented for the Go Builder motors. Since Go Builder already publishes the final number, one can trace the steps by assuming default values for the rises of channel number that is shown as 7 on this slide. The table on this slide is for the Rev HD hex motor. Once again, note that the wheel diameter is expressed in millimeters, but the final result, counts or ticks per inch, is applied in the op mode in inches, since the FTC field measurements use inches and feet predominantly. This slide illustrates the calculations for the Go Builder 5203 Yellow Jacket Planetary Series 19.2:1 motor. It is a very popular motor for drivetrains with optimal performance characteristics. Go Builder publishes the counts or ticks per rotation in the corresponding datasheet for the motor. The only calculation that needs to be performed is to multiply this value with the circumference of the chosen wheel for the robot. In this example, a mecanum with a diameter of 96 mm is used for the final calculation. This motor is present in the robot that will be used for the demonstrations in the tutorial. After the counts or ticks per inch number has been calculated using methods similar to those described in the previous slides, or the number may have simply been given to you by your coach, use this number in your code to obtain the number of counts or ticks that must be registered by each motor for the robot to travel the user-specified distance. A nominal speed value of 0.6 is the initial number, but in fact other values are applicable too. Once the robot starts the linear movement, then the code simply checks each motor to determine if the target value in counts or ticks has been reached. When all motors reach the target values, the motors are stopped to conclude the test. The estimated counts or ticks for the specified travel distance is set as the target position for each motor in the drivetrain. Since the requirement for travel movement is linear, all motors are set to the common value. The user-specified speed for the motor is also set at this stage. The control loop is a simple while loop. All motors are in the busy state until they reach their target value that was illustrated in the previous slide. Within the loop, there is no major activity while the motors keep running. There is nominal telemetry update and some system calls to yield processing to other tasks. Upon reaching its target count or tick value, a motor sets itself as not busy. When all motors are not busy, then the motors are stopped. In other words, the speed is set to 0. After estimating the counts per inch for the specific combination of motor encoder and wheel, calculate the counts or ticks that represent a given distance by multiplying the given distance with the counts per inch coefficient. There are many different key columns that can be included in a tabulation of test case log. But some of the more important ones include test case ID. This is a unique identifier for the test case. Test case direction, either forward, reverse, or turn. Expected results. This is the linear travel distance for the robot. Actual results. This is the distance actually traveled by the robot. Error. This is the difference between expected or actual. Notes. This is a space for any additional notes about the test case. The linear travel distance is hard coded in the op mode. The op mode is then built and launched. The op mode is then run. The distance traveled by the robot is recorded. The process is repeated for the next travel distance. it is important to note that the friction properties between the robot wheels and the field tiles may have an effect if either of these manifest wear and tear. Accidental wheel slippage may cause another type of variation, especially if it applies to select wheels. Also, some motors, even new ones, have incorrect Hall effect sensors owing to assembly or placement errors. It is very important to reassure oneself that the motor is generating the counts or ticks accurately upon rotation. That's all, folks. Please provide feedback in any which way you can. This presentation was prepared with assistance as noted on the slide. My apologies if I have unintentionally omitted anyone or any resource. A very big thank you to y'all. Come back to the channel soon